Well, hello again everybody, and today we're going to have a look at this Heathkit IT-12 signal tracer. So I recently purchased this signal tracer from America, and you can kind of tell that because it's still got the American plug on it, and of course it's going to be, I don't know, 110, 120 volts operation, which isn't a lot of good for the UK, but if you remember last week I did buy that step down transformer, so hopefully that's going to be used to power this. Now, I've got to admit, I don't really know very much about this particular model of signal tracer, so I'm going to take a quick guess at what the controls do. So I'm assuming that, okay, that just clicks, so there's an on and off switch. That's not very exciting. We've got a level control, which I'm sure is just volume. Seems like you can power up some external speakers here, so it's got two speaker connections. It's got a variety of connections down here, CT, B+, and P. I'm not sure what they're for. Maybe is that B+? Could that be for powering a valve HT supply? Not sure. Got another switch, looks like we can turn the speaker on and off. Got a noise button, don't know what that does yet. And quite interesting, we've got a magic eye valve down here. Magic eyes are always good for a laugh. And it also comes with this signal tracer probe, which I always think looks very futuristic, almost like a ray gun or something like that. Definitely reminds me of the rocket age. And it's got a switch on it, so basically we can listen to audio on this signal tracer, or you can flick the switch back, and I think it'll probably put a germanium diode into circuit, which we can use for RF demodulating, so we can use it to listen to the IF stage on a radio and the tuner and stuff like that. So it's also got a piece of braid on it here, which I'm guessing is to connect to our chassis of the valve radio or whatever piece of equipment we're working on. So that's our ground connection. And I'm not sure, it looks like it's got a pointy end, and I don't know, can we take this probe off the end? Not exactly sure, maybe that unscrews. It looks like it does something like that. Now you can probably see that the body of the probe's actually made out of aluminium, so of course it's conductive, and it does slightly worry me that if I was to clip this ground connection onto, I don't know, a live chassis or something, I wouldn't be in for a fun time. And of course that's made worse because the mains connector on here, it's not an earthed connector, so if you did actually plug this ground clip onto a live chassis, it's not even going to trip the fuse out or something like that. So yeah, I'm not sure whether it would be a good idea to insulate it or not. Obviously back in the 1950s or 60s, whenever this thing was built, they obviously had a different outlook on safety. I think what I'll be trying to do is we might be trying to replace this lead and see if we can ground the body of this signal tracer. That's probably my plan anyway. Anyway, shall we have a look at how we get inside it? Because I'm not sure how we do that. I'm thinking maybe it's a rear entry job. So let's see if we can get the back off it. Now, as I may have said earlier, I haven't had a look at the circuit diagram for this, so I'm not exactly sure what we're going to find inside. I do intend to download one and have a look. But I'm guessing if it is a piece of valve equipment, it's going to be of a certain age. We're probably going to have to look at replacing coupling capacitors, and I also want to see if we've got any electrolytics in here. Okay, so the back didn't come off. So there's my first little fail. Ow. Well, I can see that somebody's been prying away at the back with a screwdriver here, so I'm certainly not the first person who's tried to get inside this. Do I have to undo that screw? Or do we just add to the circuit, or do we just add to the marks on the back of this? Because somebody's had a screwdriver in here before me and they've tried to pry it off. Is that going to come off? Oh, it's actually the front that's come off. There's a surprise. Is the whole thing going to come out? Oh, there we go. There's definitely some kind of ferocious looking beastie in here. Luckily I think it is fairly desiccated. I've got no idea what it is. What sort of bug is that? Is that a cockroach? I don't know. It's quite a big one. Bloody American cockroaches here to steal our women, overpaid, oversexed and over here. Right, it's very dirty and dusty inside the back of the cabinet. I'm going to just sweep that out. God, lots of dust blowing out of this thing. Ugh. The inside of this thing is pretty well dominated by this rather huge magic eye tube, so I look forward to powering that up. That should be quite interesting. The inside is really pretty dusty, so I think we'll have to remove some of these parts and give it a clean. So we've got the main step down transformer here, so that's going to be powering the heater current for the valves, because we've got three valves here. So this is going to be generating the low voltage for the heater filaments. I don't know what the voltage will be on these valves, and it's also going to be generating the HT. Now I was hoping it would be a multi-tapped and we could maybe switch this to 230, but no, we're not that lucky. So I was also just interested to see how much room there is floating around in this thing, because I was kind of also hoping that there might be a possibility of maybe putting another transformer in it somewhere, so we could step down from 230 British voltage to 120. But I think we'd struggle to get a toroid or something like that in here. So it looks like I'm going to have to keep operating this on that step down transformer that I bought, which is fine. I mean, there's something quite nice to keep it authentic, isn't there? I wonder if we can go ahead though and replace this cable here with an earthed cable, because I think I would rather see this piece of equipment earthed rather than floating. I wonder why they didn't earth it the first time round. I wonder if there's a reason why this piece of equipment's not earthed. So I'm just going to clip onto the remnants of, like I say, the ground clip that must have stuck out of here on the probe. So let's just clip onto there. And let's just go off the metal body. Yep, so we do have continuity through to here. So if you were unlucky enough to clip this probe onto something live, well, you're going to know about it, aren't you? Because the first thing is going to happen, you're going to get a belt off the metal body here, but the whole body of this instrument's going to become live. So I think that I would actually in preference like to ground this out, although of course if we do ground it we might have ground loop problems and start to introduce some hum. I don't know, maybe we'll see how we go. Obviously back in the day they were obviously thought that risk of getting an electric shock was kind of acceptable. Not sure. So just moving on from our power transformer here, I'm just tracing the wires out, and it looks like we've got a silicon diode. So we haven't got a rectifier tube, which is what I was expecting. So this piece of equipment is obviously modern enough to have a rectifier diode, a solid state semiconductor diode, as opposed to a rectifier tube. So you can see we've got another transformer, and it's actually screwed to the back of our speaker. And what this is the output transformer, because as I think we said on a previous video of mine, the output valves here, I think that's the output valve. What's that? Let me have a look at it. It's, what tube is this? Can we see it? It's a 12CA5, a 12CA5. So this is an output pentode tube. So that's our output valve. But even though it's an output pentode, the actual impedance of this valve is far too high to drive our 2 or 3 ohms speaker. So we've got an impedance matching transformer here. Let's see what our other tube is on the other side. Okay, it's a 12AX7, which of course is I think it's a double triode, isn't it? It's typically used as a preamplifier valve. So let's have him out. Now you can't really tell the age of a valve looking at the envelope, but having said that, both these envelopes, there's no kind of staining or signs of heat on them, so I suspect this equipment hasn't really been run very frequently. Same for the Magic Eye valve. There's a little bit of splurge on the side there, which is just where the getter was ignited when this valve was manufactured. Got quite an interesting on and off switch here, in that it's well, it's kind of all very open frame and you can actually see how it operates. The terminals look a bit grubby though, so I think we'll give them a clean before we do too much with it. In fact, it looks very black and tarnished, that, so I think that needs a clean. So we will give that a bit of a clean with switch cleaner. And on the other side here we've got a 1 megohm potentiometer, which is our volume control, and it's got nice holes drilled in it, so we can spray some switch cleaner into that, can't we? So we've also got what's quite a large capacitor here, and it looks like it's actually 3 capacitors in a single can. So it looks like the model number or the manufacturer, it says 25-65, and I don't know if that's synchron, I think it's synchro maybe. It's got a 50 microfarad, at 150 volts DC. It's got another 50 microfarad at 150 volts DC, and it's also got a 20 microfarad at 25 volts DC. So quite an interesting mix of capacitors all built into that can. So I'm hoping that this capacitor will be good, because well, it'd be a shame to have to swap that out, because it looks, again, I said it looks in good condition. We'll have to power it up and test it, won't we? So just taking a deeper look into our chassis here, I can see that we've got a few resistors and capacitors. All the resistors are, you know, there's no signs of burning or anything else. Again, it all looks like brand new. We've got quite a few little ceramic disc capacitors, and again, they're generally pretty reliable, so I'm not suspecting any problems with them. And it looks as though we've got a coupling capacitor here, which the brand on it looks as though it's a brown coloured capacitor, and I think it says TRW, so perhaps my American viewers can tell me if that's a good brand of capacitor. Are they likely to go short circuit or anything like that? I'm guessing that this is actually the coupling capacitor between the preamplifier valve here and the output pentode. So it's actually very, very important whenever you, I'd almost say whenever you work on a valve radio, for example, which would probably typically be older than this piece of equipment. If you've got like a waxy capacitor in the place of this component here, you must always replace those waxy coupling capacitors, because if you get any DC voltage onto the plate of your output valve, it's going to get very hot and burn out in very short order. So I would typically replace these on site, but it isn't a waxy capacitor, it's something much more modern than that. So what I think I might do is we'll just power this up and we'll do a DC test on it. We'll just measure, and typically you should find 0 volts. You certainly shouldn't find a positive offset voltage on here, so we'll give that a try as well. Now, I'm not certain, but I think a lot of these Heathkits were designed to be built as kits. So what I think it might be interesting to do is to see if I can actually download the original construction manual for this, to actually see if it gives us any setup and testing guide. Whoever manufactured this, if it was home built, the guy obviously knew what he was doing. It's very nicely put together, so you know, well done to whoever built this back in the day. So what I've done is I've just gone ahead and I've downloaded a copy of the original manual from the Electrotania website, because I really wanted to see how this was put together back in the day. So it looks like our manual is going to cover the assembly and the operation of the signal tracer. Quite a nice photograph on the front here. It does look like quite a comprehensive manual. It does of course come with a circuit diagram. I've actually gone ahead and I've printed a circuit diagram out separately, which is a little bit bigger, and it'll be easy to read some of the values and stuff like that off it. So at the top of page 3 here, it does give us a little bit of a simple introduction and use of the signal tracer. So it says we've got a high gain position for direct signal tracing in RF and IF circuits. We've got a high gain position for signal tracing in audio application circuits. It comes with a convenient RF or audio switch in the probe body. So of course, that's talking about this switch here, and all this does is it just brings in a diode so we can actually demodulate an RF signal and just recover the audio envelope. So it says we've also got a visual signal indicator. So I guess what they're talking about here is the magic eye valve that the signal tracer's got on the front of it. Now, I don't know about you, but in the past I've had various equipment that's got these magic eye valves on them, and I've never found them to be particularly useful. Now, of course, they do look quite impressive when the aperture on the magic eye, when it opens or closes, but they're kind of not calibrated in any way, and I've often thought that the information it conveys is just a little bit meaningless. We can use the unit as a utility amplifier for checking record changes and tuners. So at the heart of the signal tracer, all it really is, it's just a high gain amplifier. So it's just saying here that we can we can plug a record deck in, a tuner or something like that into it, just to test that we're getting an output from a magnetic cartridge on a turntable or something like that. It says we can also use it for checking microphones and musical instruments, pickups and speakers. It says we can also substitute the main speaker inside the unit for an external speaker, so we can use it to check external speakers as well. And it's also got, again, an output level indicator, so I'm guessing it's maybe talking about the magic eye valve again. So within the introduction it also mentions this noise switch, they call it S3 here, and I knew that the noise switch was for detecting noise in circuits, bad joints and maybe components breaking down, but I didn't actually know how it operated, and it gives us a bit of information here. So it says here that the noise switch connects B plus to the probe lead through a resistor R14, and that the probe switch must be in the audio position for it to work. So from the description, what it's telling us, when we actually engage the noise switch on the front of the unit, it actually connects this to B plus. Now B plus will be the HT supply to the valves, and I think it says somewhere else in here it's around 100 volts. So it connects the tip of the probe to a 100 volt supply via a resistor. And again, later on in this document it says you've got to be quite careful using this, because there is enough current if you actually to touch this to get a little bit of an electric shock off it. I think it calls it a minor electric shock or something like that, but I can't really think of the last time I operated a piece of test gear which actually said, well, I suppose that's not quite true, because megameters can give you an electric shock, but I'm glad I actually read this text before just going ahead and touching this, because, well, I'm sure you lot would have got a laugh as I jumped out my chair, but just goes to show sometimes it's good to read the manual, isn't it? Because I would have just touched this not knowing it was live. But I think what we will do is we will test this noise switch when we've got it up and running, and just measure the tip voltage, and you never know, I may even give it a touch and see if I can feel anything. So you can see on the left hand side of each page here we've got this little row of tick boxes. So as you completed each task, you know, each instruction here, you would put a tick in the box, and then you'd be able to follow the assembly process through and make sure you hadn't missed any stages. Now this is an old manual I've downloaded. It's probably been photocopied or scanned in from somebody's unit when they built theirs in the past. So it's already got all these ticks in, but I think that's really nice. Now, one thing that's immediately obvious about this Heathkit is that actually the quality of the kit it's a very high quality kit. It's a lovely piece of equipment. They obviously also spared no expense in producing these beautiful engineering drawings. I think these are some of the best kind of mechanical assembly drawings that I've ever seen. They're just superb. So we've got a lovely picture here showing us how the output audio transformer is assembled to the back of the speaker, and then the speaker itself is mounted to the front panel. So here's a top view of our chassis, and it shows our switches here, our switches and our volume control. Here's our multi-stage capacitor C7. So we've got a sketch here showing the assembly of the volume potentiometer through the front panel of the equipment, and it's got a really little nice detail here showing a tab washer. And this tab washer looks as though it has a long extended tab on it, and I'm guessing that this must lock through the body of the potentiometer to stop it rotating, something like that. I'm not exactly sure, maybe we can look for that shortly. But again, just a lovely little detail there. Now, can you imagine what a massive pleasure it must have been to sit there at your work desk back in the day to assemble this thing? I've assembled lots of kit radios and things like in the past, and in some ways they're actually quite complicated, you know, especially stuff with surface mount and all that kind of malarkey. But I bet this was an absolute pleasure to assemble, and the instructions must have made it so easy. Now, of course, we haven't even tried to connect any power to this unit yet, but I do think it's important, and I'm going to take a little bit of time to review these assembly instructions just to make sure that this unit that I've got here has been assembled in accordance with the with the manufacturer's information here, because it's not unusual to buy a piece of equipment that's been messed around with, or perhaps had something connected wrong or bodged. I am going to take a few moments off camera just to have a look at the construction of this, review all the text, make sure we've got all the parts in the right place, and what I'm also going to do is I'm just going to check all the component values against the schematic, because there's not hundreds of components on here. There's probably only like 10 resistors and just 5 or 6, 7 capacitors, so it's going to be easy for me to go across and check all these. When you've only got a few components, there's no reason not to check them, is there? So let's go ahead and do that. So starting off with the probe here, we've got switch S2. So switch S2, that allows us to either directly connect the tip of the probe to the audio amplifier, or we can connect the tip of the probe through this diode and capacitor. So when it's connected to the diode, this is used as an RF demodulator. So if we've got a modulated signal, what this will actually do is the diode will demodulate that signal, and it'll just leave us with the recovered audio waveform, which will then get amplified up here. So that's the purpose of the switch and what that does. So following up, here's the switch S3. Now we mentioned this noise switch earlier, so you can see that the noise switch here, it's actually connected to our B+ supply, which is, according to this little box here, around 114 volts. So we're actually putting 114 volts on the tip of our probe, but it's actually being current limited by this 68k resistor. So if we just take our 114 volts B+ and we actually divide it by this resistor 68k, 68, what that's going to give us, that's going to give us the current that can flow into the tip of our probe here, which is 1.67 milliamps. Well, I'm not sure, but I think you're going to feel 1.6 milliamps with 100 volts behind it. I think you are going to get a tickle from that. It just kind of shows that back in the day, they weren't afraid to give you a bit of a buzz, were they? So it's obviously very important that we actually check that this 68k resistor is 68k or above. What we don't want to find is that maybe this has gone low in value or short circuit, because then we're going to get no current limiting and you could probably receive a really nasty shock from the tip of the probe. As it is, you'll probably just get a tingle, but without that resistor in place you could get a really nasty belt, so we need to check that. So following the circuit up, we come to our first audio preamplifier stage, which is made up of our AX7 valves. So our signal comes in via our DC blocking capacitor, and the next component it sees is our volume control potentiometer. Now we've got one end of the volume control potentiometer that's tied down to the earth line, and the signal comes in at the other end, and then the wiper moves between the earth end and the incoming signal end. You can see what looks a little bit like two valves here, but this is actually just one valve. It's our 12AX7. So if you was to look inside that valve, you'd actually find that it's got two triodes inside. So you can see the two triode stages here. Then we've got R2 here, which is a grid leak resistor, and you can also see that we've got some negative feedback here in the form of R4, which is a 1k resistor. The anode of our first triode, it's coupled into the grid of our second triode via a resistor here, which is a 0.005 microfarad. So we've got a few capacitors here. So we saw one there and one down here. Now the job of all those capacitors is DC blocking, and I may have said earlier, it's very, very important that we don't get any DC into the grids of any valves. So what we need to do is we need to check that we've got no leakage across any of these capacitors. Now the schematic also indicates the plate voltages for both of our triode stages, and this one's around 80 volts and this one's around 76. So that, you know, that's very approximately half the B+ rail. That's approximately half. So this is actually set up in Class A. It's a Class A amplifier. The output from our preamplifier here, it's coupled into the grid of our 12CA5, which is our output pentode valve. So it's coupled into the grid there via C5. Again, want to keep any DC off our grid here. Got another grid leak resistance, and the output pentode is being biased via our R8 cathode resistor, which has also got this AC bypass in it. Sometimes these drawings can look a little bit confusing because you expect the high voltage should be coming in at the top here, which it isn't. The actual high voltage, the anode to our valve here, it's actually being fed in via the windings of our output transformer. So that's how that works. Our B+ comes in here and it goes through the transformer, and then it comes into the anode of our output pentode. And we're also splitting a little bit of that off. Again, we're putting a DC blocking capacitor in, and that's also coming down here, and that's going to feed the grid of our magic eye. So that's going to make you know, the light dance on it. That's going to modulate the light output from the magic eye valve. So there's our mains on and off switch, and that's just providing the primary of our transformer with power. Now the secondary has two windings on it. We've got this little small winding here, which is shown as being a 12.6 volt winding. So that's supplying all the filaments, that's all the heaters of our tubes. So that's supplying the heaters to V1, V2 and V3, with V3 being our magic eye tube. And the other secondary in our transformer is actually providing our high voltage B+, and you can see it's actually, rather than using a tube rectifier, it's using a silicon diode, and we've just got one of them. So this is a half wave rectifier circuit. Now because it is a half wave rectifier, that's going to have more ripple on it than it would if it was a full wave circuit. I'm guessing that they just did it half-wave because that was probably cheaper for them just to use a single diode. But it does mean that you have more ripple in the circuit. So you can see here we've got these two capacitors that are connected together via this 10k resistor. So what these do is these form a low pass filter, and it's just designed to smooth out the ripple from our half-wave rectifier here. Now both these capacitors, they're actually installed in the same can. And interestingly, the third capacitor that's in the same can is actually not connected anywhere near the power supply. It's actually the cathode bypass capacitor up here in our output amplifier circuit. Sorry about that, everybody. I do talk a load of old cobblers, don't I? So what I think I'll do now, just using my DVM here, I'm just going to go through on the ohms range, and I'm going to just roughly check all the resistors, make sure they're roughly in tolerance, and I'm also just going to check out any capacitor I see. It's not a leakage check, of course, really. I'm just looking for any gross short circuits, but I'm going to go ahead and do that. So the first resistor I've spotted is our smoothing resistor here, which is a 10k, and that's coming up as 10.7, quite good enough. The next one is a 1 megohm resistor, which is across the plates of our Magic Eye valve. That's coming in as 1.1 meg. You can tell that really an awful lot of thought has gone into the mechanical construction assembly of this thing. It really is just very nicely put together. So you can see I can just remove that Magic Eye assembly here and get access to the whole of the underside of the chassis there, so that really is quite lovely. I'm just probing R14 here, which is our current limiting resistor for that noise circuit, and that should be 68k, and it's actually coming in at 75. So the first three resistors that I've measured so far, they've all been a little bit high. Again, I'm not really going to worry about the difference between 68k and 75. In an application like this, it's just current limiting, it isn't going to have an effect. The next resistor I'm going to check is our grid leak resistor, which is on the first stage of our triode preamplifier. Again, that's coming in a little bit high, should be 330, and it's coming in as 360. The next one is the cathode bypass, which should be 1k. Which is 1k. The next resistor I'm going to check is the anode load of our first triode. So that's actually coming up as about 110k. Well, that should be 68, so that's well out of tolerance. So I think what we'll do is we'll have that out and replace that one. Now for this style of resistor, I'm not surprised that we're getting these high resistance values. They're going over value. That's kind of the common sort of failure mode for these as they start to get older. Now looking at them, there's no burn or physical looking damage to any of these, so you know they've not been damaged in any way. In fact, this doesn't really look as though it's had very much use at all. It's just the fact that the chemical composition that makes up these resistors, it just changes over the years, and the resistance value tends to go high. Now I'm hoping not to have to change every resistor. I'm just going to make a judgment call as I go of what I'm going to change and what I'm not. I don't think 60 ohms is going to help. Help if I got the right resistors out, wouldn't it? Duh. Kind of wondering if I've got anything that's just a little bit vintage that might look like what's already in there, but I think probably not. Well, it looks like it's... I think I'm going to choose one of these high stability carbon film resistors for no other reason, but it's brown. Because obviously we need to put a brown one in, because a brown one will work better than the blue one. I suppose I probably should just sense check our wattage, because these are only 0.25 watt resistors, that's all I've got. So our B plus voltage is 114 volts, and our plate voltage is 80. So we've got 34 volts being dropped across R3. And if we do V squared over R, that's going to give her our wattage. So 34 times 34 equals that, divided by 68,000 equals 0.17 watts. I'm just going to check the resistance using the ohm meter, because my eyes aren't as good as they used to be. Yeah, so 68, 70k, quite good enough. I've got to admit, I think whoever built this actually did a really nice job of it. Nothing wrong with it at all. So it just had some little glass wrapped insulation around the legs of these resistors, so I'm just going to put that back on. Okay, let's double check that. We should have about 68k between these points now. 70, good enough. So I'm going to go ahead and I'm going to finish checking these, and if there's any work that needs to be done, I'll bring you back for that. While I've got it all open and access to everything, I'm just going to give all the controls a little bit of a squirt and a move round. So the operation of this potentiometer does feel a little bit smoother for having some cleaner sprayed into it. Let's just do the on and off switch at the opposite side. That seems okay. Seeing as we've got access to it, we may as well just check our rectifier diode here. Okay, it didn't conduct in that direction, it should conduct in this one, which it does. 0.5 volts, that's about right. Just giving the chassis a little bit of a wipe over with a deoxit cleaner just to remove again some more dust and dirt off it. So I think what I'll do in the future is I think I'll go ahead and I will replace this mains cord with a free core cable, one that's got an earth on it. Now unfortunately I don't have one of those that has an American plug on it, because I am going to plug this into my my American voltage converter. So I need to get an American 3-pin plug, because at the moment it's only got a 2-pin plug on it, so it's not earthed. And I was thinking about that. I mean, I think before I was talking about the problem if you actually probe a live circuit with this, then potentially the body of this equipment could become live if you were clipped the ground clip there onto a live part of the circuit. But similarly, if we got a fault with the transformer here, maybe a winding breaks down, comes in contact with the frame, again this body of this equipment could become live to 230 volts in line with the main supply. So that could be quite dangerous when you're holding a metal probe or something like that. So I think that this needs to be earthed. So I think until I do that though, what I'll do is we'll just run this via my isolation transformer, which will give us a little bit more protection. So I think what we'll definitely have to do in the future, I'm going to have to get hold of a free core mains flex from America with an earth plug on it, and we'll replace this 2-core cable with an earth cable. So of course it's perfectly normal for the knurling on the control knobs to be absolutely filthy, and what you need is you need something to clean out all the crud and the detritus that's built up over many years. Now of course we both know that there's a perfect tool for doing this, and here it is, because my wife has gone shopping at the moment. So we'll just give the knobs a little bit of a scrub with a toothbrush, and I'm sure they'll come up a treat. And I think I'll just take the opportunity to just lube the end of my shaft. So I'm off downstairs to use the kitchen sink to give our knobs a nice good rub-a-dub scrub. I thought that I was going to get away with just changing one resistor, but I've also just measured this cathode bypass resistor here. It should be 330 ohms, but it's actually coming up as 400. Now I am actually going to change that one, because this is part of the bias circuit for the output pentode, so it's actually important. So I'm going to go ahead and change this. Annoyingly it's a bit difficult to get to, but oh well. So one side of the resistor is actually connected to the bypass capacitor, which is inside this kind of multi-capacitor can here, and the other side is just to the chassis ground. But yeah, it's just in a bit of an awkward place to get a soldering iron in and stuff like that. I think what I might do is just solder it onto the leg of the old resistor, because I think that's about all I'm going to be able to get access to, just to get my iron in there. Now I'm going ahead and I'm putting I don't know if this is a 2 or 3 watt resistor, I'm putting a much bigger resistor in than it actually needs, and for no other reason that's just all I had in 330 ohms, so it doesn't need a resistor as bigger in wattage value as this one. Unfortunately it's just all I've got in the box at the moment. I think we're about ready to just power this up for the first time, and what I'm going to do is I'm going to power it up without any valves in, and because this has got a silicon rectifier, what we'll do is we'll turn the voltage up very slowly and we'll give these capacitors a chance to reform, because hopefully they will. This isn't such a very old piece of equipment, and I'm hoping that these will be a good quality electrolytic, and yeah, I'm hoping it's going to be good, but it may not be. So we'll power it up gradually, and well, we'll see how we go from there. I think before I do power it up though, I'm just going to short the live and the neutral connections together. I'm just going to do an earth leakage test, an earth insulation resistance test between the chassis here and the live and neutral, just to make sure the transformer's good. So the way that we do the insulation resistance test, you need to short the live and the neutral connectors together. So just take a link wire, short them together, take one side of your megameter, put it onto the main supply here, and put the second probe onto the chassis of your piece of equipment. Choose the range you want to do the test at, which I'm going to do 500 volts, and press the button. And here we're getting an infinity reading, so that's good. That means that there's nothing wrong with the insulation of the transformer. I should also say it's important that the piece of equipment that you're testing is switched on, and we should also just do a bit of a sense check. So I'm just going to clip it on there because I want to make sure it fails, which it does. So we've just checked that our instrument is reading correctly as well. So hopefully when we power this up, there's no short circuits here in the wiring or on the power transformer, so the body of our equipment shouldn't become live.